In this video, we're going to be talking about how to use this little Java applet here, which is a very useful tool that you can use in order to represent molecular structures both in 2D and in 3D. In order to get this program working, the first thing that you'll need to do is to go to this website here. If you don't remember this URL, if you go to your favorite search engine and simply search for PHet, this website will be the first hit on the search engine results. Now, this is a very useful website that not just covers a bunch of Java applets that can be used with chemistry, but also a number of different subjects. In order to find the simulation we're looking for, though, go to the Simulations tab and scroll down to Chemistry. When you do, the simulation that you're looking for is the one that is called Molecule Shapes. And if you click on this, you will be prompted to download this, and once again, because this is technically not a program, it's a Java applet. As long as your computer has the latest version of Java, it should work on both Windows and Macintosh computers. When you do that, there's no install that's retired. The program, when opened up, will look like this. You should be given a prompt to build your own model or to look at real molecules. What we're interested in is being able to build models that look like this. So this program is very useful if you don't have a background on what 3D molecular structures look like. So let's say that we wanted to build carbon dioxide. We know that the central atom of carbon dioxide is carbon, and we know that there are two oxygens, each with double bonds. So we simply click on the peripheral atom with two bonds here, and there's one atom with a double bond, and there's two atoms with a double bond, and we can see, even without labeling the bond angles, that this angle here is approximately 180 degrees. But if you're not sure exactly what the angle is, if you click this option here that says Show Bond Angles, it will label what the angle is here. Now, as you learn about 3D Lewis structures, most people will recognize that Lewis structures get complicated in 3D as soon as we have an AX4 molecule or higher, which means a molecule that has 4 or more attachments. So if we wanted to know what the structure of CH4 was in 3D, well, here's our central atom carbon, and let's add on 4 single bonded hydrogens, 1, 2, 3, 4. Let's get rid of the bond angles for now. And if we orient this molecule, let's orient this molecule so that this top bond here and this bottom left bond here are basically flat. So if you were to draw these bonds here in 2D, each of them would be flat. Now, if you look at this hydrogen here, if this hydrogen and this hydrogen are flat, then this one here is coming towards you. It looks like it's pointing towards the screen, whereas this hydrogen here is pointed backwards. So we can see here, starting with AX4 molecules, these are the first molecules where we see that the molecule actually has 3 dimensions. And if we wanted to see that all 4 of these angles are equal, if we click Show Bond Angle here, it shows that all of these bond angles come to 109.5. According to Vesper theory, this is the biggest angle that we can make such that each of the 4 bonding pairs are as far away from each other as possible. Now, there are a few other patterns that we can see. If we wanted to make a molecule that has an expanded valence shell, we can, if we wanted to make phosphorus pentachloride, PCl5, again, that's a central atom with 5 single bonded chlorines, 1, 2, 3, 4, 5. We can see as soon as we get to AX5 molecules and above, there's a little pattern that becomes very observable. We can see that this side atom and this side atom form a 180 degree angle with each other, and these are what we call axial atoms because you can actually rotate the other 3 atoms on an axis such that, and I've bent this molecule a little bit, such that these three atoms form a 360-degree arc around the two atoms. And these three here are what we call equatorial atoms, because if you draw a circle around, it forms 360 degrees. If we want to measure these angles, we can see that this angle here kind of looks like 180 degrees, with the angle between this top atom and the atom over here being 90. And then if these three atoms that form a circle, the equatorial atoms, are 360 degrees, then we would expect that each of these angles here around these, let's angle it such that we can see them more clearly, these angles look like 120 degrees, and if we show bond angles, that's exactly what we see. We see 90 degrees between one of the axial atoms and each of the equatorial atoms, and then if we tilt this to see the bonds between the equatorial atoms, we see that they are 120 as well. Anyway, this is something that you can play around with. One last thing, let's say that you're dealing with a molecule that doesn't have only bonds, that has lone pairs. Let's say that we wanted to build the structure of water. So we know that water is an AX2E2 molecule because the central atom oxygen has two hydrogens bonded to it, but it also has two lone pairs. So if we wanted to see this representation shows us water. So we can see that the geometry of a water molecule is very similar to the geometry of an AX4 molecule, only with these two lone pairs in an AX4 molecule, these would be bonds that connect the peripheral atoms to the central atom, but since there are no bonds here, these would be lone pairs. So again, we can see the 3D geometry here. These bonds here would be planar in this case. This bond would be flat against the computer screen pointed up. This one would be flat pointing to the bottom left. We see that this hydrogen here would be pointed backward and this hydrogen here would be pointed forward. And if we want to show the bond angles, again, we see the same bond angle that we would see in an AX4 molecule. So that's your introduction to the PHet molecular shape simulation. The more you play around with this, the more intuitive this becomes, and it becomes a very useful tool to use in terms of being able to predict the geometry of large and more complicated structures that actually have their atoms in 3D.